right. I feel I've got pretty big shoes to fill or to carry on with this, but I'll start by saying my name is Drew Phillips. Title of my presentation is The Where of Dry, and I'm going to be talking about tracking all agricultural droughts through space and time. So I want to pick up a little bit from the last presentation by using an example of Aware's resources to answer a question. In this phase of my project, I've used the grid script that Kale developed, and I've also identified ways to incorporate the Aware package in future versions of this project. So this project idea kind of came about from two related problems. First of all is we know that droughts are incredibly destructive, but a lot of times, especially here in the US, we're spared the worst effects of their droughts, the worst of their effects. So I was curious, how can we bring this, the effects of droughts to a local level? And the second issue I tried to address was it's hard to describe the area that's impacted by droughts. On the right, I've got a graphic from the US Drought Monitor, which is a combination of quantitative data that's been judged by experts, but the boundaries of these droughts are pretty approximate, somewhat arbitrary. So overall, I was curious, how can I accurately describe the extent of a droughted area, and how can I communicate those results on a local level? So I'll talk about the metric I use really quickly. It's called P over PET, and it's often used for agronomics. In this ratio, P stands for precipitation and PET stands for potential evapotranspiration. You can kind of think of it as a ratio that has water in divided by water out. So the closer that value is to 1, the more completely groundwater is recharged in any system. On the right side of the screen, I've got some approximate thresholds, and at or below these thresholds, a lot of plants start showing the effects of drought, mainly water stress. So for many crops, you'll have a P over PET of 0.6 to 0.8. Forests and rangeland are a little bit more resilient. You can see a ratio of 0.4. My project, I chose 0.5, which would correspond to a fairly severe agricultural drought. But I also wanted to kind of test using pretty high standards just to see how my script would perform. So I'll go really quickly over the method that I used to come up with my graphs. First of all, I used Kale's grid script to draw a grid over the area of interest. And then using Aware's API, I was able to get the precipitation and potential evapotranspiration values for each square. And then I entered that threshold of 0.5. So from that threshold, I could then determine whether each grid cell was droughted or not. And then I wrote code to draw a polygon over the droughted area that shows the smallest contiguous droughted area. So one of the things you might notice is the droughted area actually extends beyond the borders. This is because the grid cells I chose, every one touches the county. But I understand that this can be a little bit confusing, and it's something that I can address in later versions of the project because it's a little hard to interpret. The variable I chose was Josephine County, Oregon, which is a rural county that's just north of Northern California in Southern Oregon, and it's been experiencing severe drought since about April of this year. The time period I chose was the approximate growing season from May to the end of October. So on these two graphs, you can see a comparison of drought extent for 2 years, from 2016 to 2019. And in 2016, you can see a large droughted area extending over the eastern part of the county. And again, this is the smallest area that covers the largest cluster of droughted cells. And in 2019, you can see that the entire county is droughted. So from these two figures, we can tell that the drought extent using this variable has increased since 2016. And the interesting thing is values for 2020 will be available in several months, and I plan to extend the analysis to 2020 as well, just to kind of complete this portion. So the other thing I was interested in looking at is drought intensity by year. And in this one, I looked at the average P over PET in the droughted area. And I chose this area instead of choosing the entire county, so I could try to focus on the effects of droughts themselves. So you can see a decrease, though not a linear decrease, since about 2016 in the average P over PET of droughted areas. Once again, a lower P over PET value indicates increased aridity. So you can tell that the droughted area is getting larger and it's getting drier. I've got two rough research directions, kind of divided them these categories of statistical and comparisons. For statistical, I really want to look at the zonal statistics to find land use changes in droughted areas. And in terms of comparison, I'm really interested in seeing how droughted area relates to fires and fire risk. So with that, I'm going to end my presentation, say thank you, and open it up to questions.